The solution for comprehension assessment test number 3 and strength of materials for spring 2014 is as follows. We're going to go through these pretty quickly, so if you want to see details, just please freeze frame and you can see the details. In this first item, you actually have a little bit of a trick kind of question. They're all 4 rectangular sections, they all have equal area, and they all have equal applied shear, transverse shear. So now you're selecting the section that has the largest transverse shear stress, and briefly explain why. And the way you do this is that, hey, tau equals VQ over IB. V is the same for all of them. Each of them have height H and width B symbolically. And so then the key is that we have the max shear stress at the neutral axis. And so when you go calculate Q over IB, you're going to get, well, H over 2 times B for the area, and the moment arm is H over 4, so a BH squared over 8. I is equal 1/12 BH cubed. Work that all out, you actually get 3 over 2 BH, and BH is the area. What you really get is that tau max for a rectangular section equals 3/2 V over A. And since they all have the same V, same A, they actually have all the same max shear stress. So it's a little bit of a trick question in that kind of regard. We'll talk about how the partial credit worked on these problems in class. Right, and then the second item actually has a little bit of a poor grammar in there. It's a little odd. That's my fault, going a little too fast here. But the one clear, absolute crystal clear answer here, since transverse shear stress is what we're talking about through the first 3 items in this test, and that's a big item in this entire exam, is that we get this parabolic distribution of the transverse shear stress, 0 at the outer fibers. So neither one of these, C and D, can be right, and A isn't right because of the variation. Then in item 3, we just do the actual real calculation that tau equals VQ over IB, given what the shear force is, we're given what the second moment of area is, and with that then we're just below the web flange intersection. So that means our B is 1 inch, and that the area that we're dealing with is this rectangle up top. And so we go 5 inches from the neutral axis up to the bottom of the web flange intersection, but then we got to get that additional inch for the total moment arm there of 6 inches. And then of course you do the rest of the math there. Right? For item 4, we're now into plane stress situation. We're asked to find the principal stresses. That means the maximum and minimum normal stresses, not the maximum shear stress. That's not a principal stress. Right? And so here the quickest way to do this is just to begin to plot out Moore's circle. Big key that a lot of people sometimes make a mistake on is forgetting that compression has to go on the opposite side of tension. I've chosen to draw tension to the right, compression to the left, so calling compression negative. And so when you get a final answer here and working out the right triangle and the average, you got to come along and say, okay, I got a minus sign here, and so that ultimately means that the answer is 2.27 KSI in compression, and the other one is 3.27 KSI in tension. Then we get the another plane stress problem, and we're asked for the specific situation of which Moore's circle is most consistent with this state of plane stress. Note that the 2 normal stresses are both in tension, so that when we go to plot Moore's circle, we're going to be going from 1000 up to one of the 1000 shear stresses, and then down to the other one. That these are vertical, and this is the only Moore's circle that this can possibly work out with. R turns out to be 1000. Moore's circle turns out to be tangent to the vertical axis. In item 6, yet another plane stress problem. We're given Moore's circle and the principal stresses, and now we just got to work through and find out what the sigma x and sigma y are. Right? And so you just got to go through, hey, I know this value, I know that value, those are the givens. I can then come in and find geometrically where the center is, or the average of those two are located, the geometric average, and then, or arithmetic average that is. And then I can find the radius at 901, That's the horizontal distance, but that's also this radial distance up from the center to point H. Now I can use, given I know what the angle is, I can figure out by right triangle, what this little fraction of it is and also what the height is. That turns out to be the shear stress that goes along. And then you just got to pattern match correctly. Key thing here is that point H is a horizontal plane, not a horizontal normal, but a horizontal plane. That's what we were doing in our notes. Yes, that's somewhat arbitrary, but that's what we've been doing in our notes and in class with the H and the V. And then notice the V has actually got 0 right here. You could calculate it, but it turns out to be right there on the 0 as well. So we end up then with the state of stress that you see here. Normal in the vertical direction is 1500, and then in the horizontal direction we have 0 normal stress, and then the shear stress is plotted out as shown at 500 magnitude. And no, there aren't any units in this particular problem. Item 7 is a thin wall pressure vessel problem. Very straightforward. Maximum tensile stress in a cylindrical vessel, the hoop stress will always be larger than the longitudinal stress, and so you just plug in the numbers appropriately, converting from the diameter from feet to inches, so you have inches over an inch. And then you really should be using the interior diameter. Here the ratio is such that you really don't get much of a difference. It would have been 7.0 to be more accurate than the 7.2 that's there, but that's the one that's closest. And then item 8 is kind of a little bit of a weird problem. The big thing there is to not only look at, you've got 4 different assumptions that are going on here, but you also got to look at what the text and verbiage is. And although geometric discontinuities might be a big thing, you can't really say that one that has liquid really has more access holes and larger access holes. That's a pretty erroneous kind of a statement. In other words, this is all hogwash going mostly at the back end of this. And so when you're looking at the one that's most likely to be the valid, somehow the most complete, you do get this one that's A. That is sort of the winner of them all. And although even a 20-foot diameter spherical tank, you really don't have a huge PSI difference in, say, water being in there, it's still, depending on what the overall pressure is in the tank, that can start to be significant. And again, this statement here has overall the fewest really crazy stuff that might be in there. And then finally, well, not finally, but item 9 and item 10. Item 9 is a combined loading problem. Straightforward, sigma equals P over A plus an M over S. We're looking for compression on both sides, or the max compression total, that is. And so we have this net axial stress from P over A, that's 50 kips over the area, and then sigma equals my over I, but we want the maximum, which will be at the outer fiber over here to the right, so that's going to be M over S. If you want to do MC over I, you can certainly do that. You're given the I, you're giving the D, so C would be half of that. Work that out and you get a D value, or excuse me, an answer of 29.25, or pretty darn close to that. And then finally we have one more what looks like a cylindrical pressure tank, but actually it's got a whole bunch of stuff involved. We're looking for the most consistent stress block for the plane stress condition. We have both thin wall pressure vessel situation going on there, but we also have a torque that's being applied. So from the thin wall pressure vessel theory, we're going to get a hoop stress for the cylindrical thing that is twice what the longitudinal normal stress will be on the longitudinal axis, and then we're going to add to it the torsion that goes along to it. So that direction is key. It has nothing to do with right-hand rule convention from the standpoint of how you've set up your coordinate system for the global thing. Instead, you got to think about how physically what's going on in the stress block. That's what we're trying to represent, and that's why answer B is the clear-cut correct answer on the last item. So again, we'll talk about partial credit and how that worked when we get back into class, but you have some sense now of what the correct answers are on CAT number 3.